Thanks for that introduction, and thank you very much to Boomity for inviting me today. So my group at Texas, we think a lot very generally about the question of what makes certain kinds of systems intrinsically easier or harder to predict. And on some level, this is kind of an obvious question to present to a group like this one, because in dynamical systems, we're taught that we have a very good understanding of what makes certain kinds of systems predictable or not. Right, so we've all heard the lore that if I have a system that I know has underlying chaotic behavior, usually there's very well-defined ways to quantify how far into the future I should expect to be able to predict that. Usually something like the Lyapunov time or maybe the turnover time or something like that should bound how predictable the system is. However, if you go to basically any other conference, usually when people talk about predictability, they usually mean something very different. So a lot of the time in other branches of the sciences, but especially in biology, when people talk about predictability, they're really talking about whether we have access to enough information to reconstruct the information I need to even build a forecast model in the first place. So in other words, if I'm dealing with some weird biological system, I might not necessarily care whether the underlying system is chaotic, because what I really care about is whether my measurements have enough resolution to learn whatever the state variable of that underlying dynamical system is. So in other words, in prediction, there's sort of this contrast between intrinsic predictability, which is a property of the underlying system, and observability, which is really a property of our measurements. And there's a lot of different examples of this in biology, but I think my favorite is gene expression, where oftentimes biologists are trying to understand regulatory networks, which have on the order of a dozen transcription factors interacting. But in a typical biological experiment, we're doing something like microscopy. So our actual measurement is something like 3 fluorescence channels. So biology really exists in this limit where we have very low dimensional measurements, but our actual dynamical system is higher dimensional. So we have this observability limitation. So it turns out that if you dig a little bit deeper into the lore of dynamical systems, there's actually a nice way to connect these two ideas, this idea of intrinsic predictability versus sort of observability limited prediction. And the idea is that I can think about the process of observing a chaotic system evolving as something equivalent to sampling a really complicated probability distribution. Okay, so if I have some really complicated probability distribution and I don't necessarily know the underlying structure, I can always try to sample it. And as I sample it over time, I start to feel out where the modes of that distribution are, something about the geometry of the shape of that attractor. It turns out that you can think of dynamical systems the same way, which is that if I build some really complicated turbulent simulation, I might be able to say very general things about what I expect that simulation to do, but I don't actually know what specific patterns of eddies or whatnot I'm going to see in my simulation until I actually do the simulation itself. Another way of saying that is I might be able to say very general things about what my attractor looks like due to conservations and things like that, but I don't actually know what points lie on or off the underlying attractor until I've actually simulated the system over time. So there's an old result from dynamical systems that actually makes this correspondence exact, and it basically says that as I have a system that gets more chaotic, so as higher Lyapunov exponents, the rate at which I gain information about the points that are on or off the underlying attractor is proportional to that number. So in other words, the more chaotic a system is, the more turbulent my simulation is, the more chaotic my pendulum is, the faster the rate at which I gain information about what points lie on that system's attractor. So I think that this is a really cool idea because it's just that maybe we can take almost a probabilistic view of dynamical systems where we think about this question of gaining information about future states as something analogous to a sampling problem. Okay, so based off that idea, my group has been thinking a lot about ways that we can take probabilistic ideas and apply them to dynamical systems. So first I'm going to talk about my group's efforts to maybe talk very broadly about what dynamical systems look like at large and even to try to map the space of different chaotic dynamical systems. And then I'm going to return to this question of predictability and trying to figure out what makes some kinds of systems intrinsically easier or harder to predict. Okay. So a couple of years ago, as something like a pandemic hobby, I started putting together a database of basically every example I could find in the published literature of a low-dimensional chaotic attractor. So this includes everyone's favorite systems like the Lorentz attractor, Rossler attractor, all this stuff like that. But it also includes a lot of very domain-specific examples. So the way I put this database together is I quite literally just dug through old papers, implemented them, checked to see if they actually did what the author said, and sort of rinsed and repeated. So I don't have quite the scale of something like ImageNet, but it gradually is growing over time as people suggest new systems to me. So beyond things like the Lorentz attractor and the Russell attractor, there's a lot of examples from fields like neuroscience, which has a lot of low-dimensional chaotic spiking models. There's a couple of examples from astrophysics, climate science, and I've tried to, as best I can, sample a bunch of different fields here. So in total, right now I have 135. It gradually grows over time as people suggest new systems to me. And the point of doing this is to maybe be able to say something at scale about what chaotic dynamics look like, and maybe start to say things about how we compare systems beyond just their Lyapunov exponent. Okay, so when you have a big data set like this, there's a lot of differences among systems. So I've tried to align the systems as best I can. So for example, all of them have been scaled by their dominant Lyapunov time, Lipschitz constant, stuff like that. So I've tried to standardize the data sets so these systems aren't just completely incommensurate with each other. Okay, so when I do this big collection of systems, on some level, I just start out with a giant list of equations, which isn't necessarily useful in itself. So I wanted to see if there's a way to maybe quantify how these different systems are related to each other. Because you can guess by looking at it that these aren't totally independent systems. A lot of the systems look related to one another. So I wanted to see if we could maybe quantify that a little bit more rigorously. So for example, I have a list of systems, but I know that every single one of those systems has a different Lyapunov exponent. So that's one number that I could use to compare these systems. It turns out if you dig into the time series literature, there's a bunch of different ways to extract invariant features of dynamical systems. So we used an automated method to measure around 700 different features per system that more or less try to quantify how these systems are related to each other. So these 700 features, they include things like Lyapunov exponents, things like various measures of entropy, fractal dimension, all these different things that people use to compare dynamical systems. And the point of doing that is that we go from having a giant list of equations to really having a vector in a super high dimensional space of possible invariant features that differentiate systems from one another. Okay, so I have all these systems for the literature, and for each single one of these, I have a giant vector in some high dimensional space of possible properties. So I don't know offhand how to visualize a 700 dimensional space. So what we're going to do is we're going to take each of these very high dimensional vectors. I have 135, one for each system. And we're going to visualize those in just a two-dimensional embedding. And I'm using UMAP here, but you could use your favorite embedding method if you prefer. And so when you embed that, you get this plot where every single point is a dynamical system, where they've been related to each other in this space based off of this vector of invariant properties that may or may not differentiate them from each other. And one of the things that pops out is kind of what you'd expect, which is that around the time that Lorentz publishes his original paper, a bunch of other people publish very similar scroll-like attractors. And so this unsupervised embedding actually clusters them all together. They actually all kind of pop out in the same region of this parameter space. But you also see some slightly less expected things pop up in this embedding. So for example, a lot of different chaotic models that people study have sort of a fast-slow time separation. So there's a lot of models where you have some slow periodic forcing that then causes chaos due to fast relaxation dynamics. A lot of climate models do that. And spontaneously, all of those models cluster together, suggesting that even if you don't know anything about the history of the underlying equations, the actual properties that you extract in this unsupervised way manifest in how these dynamical equations relate to each other in this embedding space. So I think this is kind of cool because it means that we can maybe go from saying very general things about this list of equations to maybe try to say more precisely how different kinds of chaos are related to each other in this space. Okay, so the issue of having a space like this that people always point out to me is that I have these big blank spots, right? There's these regions that are very clearly don't have very high density of systems. And so one question would be whether that tells us something about what kinds of dynamics are possible, or whether this is just kind of a sociological phenomenon because people haven't studied systems in that space before. So what we'd really like to do is go from having this space of equations that people have published so far to maybe trying to understand more generally what the density of these equations might look like. So can we take this set of equations and actually discover new equations leveraging what's been done before? Oh yeah, sorry. So I have these 700 dimensional vectors where it's like Lyapunov exponent, fractal dimension, and a bunch of other features. So I want to take that and embed it in 2D. I could use something like PCA, but instead I'm using UMAP, which is a nonlinear version of PCA. And you can think of UMAP as it preserves the k nearest neighbors. Yeah. And what's it? Oh, the color, I just did an unsupervised clustering just to see what groups are there, yeah. Yeah, so that's what these error bars are, is I do a feature dropout to make sure that this is a robust embedding. Yeah, good question. Okay, so can we leverage this space of equations to try to find new equations, right? Can we use what's been done before to find new things? So it turns out this sequence of operations I'm doing is pretty non-invertible, right? Because I'm going from an equation to a trajectory to invariant features to embedding. But it is actually continuous. And so you can exploit that by using the most obvious trick, which is I can take any one of these equations and just apply some small perturbation to the parameters in it. And as you can imagine, because everything I'm doing is continuous, if I make a small enough change to a parameter, I should get a small perturbation to the attractor, and I'll see a small change in the embedding. And so if you wanted to search locally in this space, you could imagine just taking one of these points, changing the parameters in the underlying differential equation, and just seeing how you change in that space. The problem with doing that is that we know that these are nonlinear systems, so you inevitably will hit a bifurcation frontier. So if you want to do a purely local exploration around any one of these points, you don't actually get that far relative to the size of the space because you just bifurcate and the chaos goes away. So instead, if you want to search more generally, you have to get a little bit more creative. So my group has been right now using some tricks from the symbolic regression literature to try to recombine systems using genetic algorithms. This is a pretty inefficient search procedure because there's no a priori reason to believe that this would work. But if you're willing to throw enough compute at it, you can very gradually find new kinds of differential equations that exhibit long-term chaos. So we're very gradually starting to fill in the dark spots in this map and find new kinds of chaotic systems. So this is something that we're excited about because it maybe says that we can ask questions more forcefully, not just about single dynamical systems and their properties, but maybe more broadly ask questions about how things vary across all these different systems. Okay, so one of the nice things about having a space like this is that even if you're not that interested in dynamical systems, you're not someone at this conference, you're maybe someone from the biology community who just wants to study dynamics, you can use a space like this for just general purpose time series analysis. So I mentioned that I have this transformation where I take any long trajectory and I sort of put it as a point in that space. You can actually do this with any time series you want. And so one of the things that my group does is we take small time series that pop up in a lot of classification tasks and things in biology, and we try to embed them in this space to see what dynamical systems they're closest to. And the reason that might be useful to you is because these dynamical systems, they have this generative property where I can always just sample new points from them. So you can actually generate very large collections of data that in some sense mimic a smaller time series problem in the sense of having similar invariant properties. And so there's a lot of things you can imagine doing with that, but we've just been doing transfer learning, where we have some tiny problem that's not appropriate to use machine learning on. We embed it in the space, generate this giant surrogate data set using these dynamical systems, train a large model, and then just use that for feature extraction. And this actually works surprisingly well for just general purpose time series classification. And the point of doing this is that it really underscores that if you have a space like this, you can start to ask really pointed questions about how you map that space and how you navigate that space for general time series problems. Okay, so that's this space of different dynamical systems that we have. So we're going from a single system like Lorentz to this large collection of 135 systems. And so now we're maybe in a position to ask more specific questions about what makes certain kinds of systems easier or harder to predict. So in order to do that, we're going to make a very large-scale experiment where we're going to try to test a bunch of different forecasting methods on these different dynamical systems. So the way that I'm going to set up this experiment is that I have 135 different dynamical systems, so each of those is like a separate task. And then for every single one of those systems separately, I'm going to train a whole bunch of different forecasting models. And I tried to sample a bunch of different fields here. So we have things like autoregressive models, which have been around a long time. We have a bunch of models that are of particular interest to folks in this audience, for example, things like reservoir computers, next generation reservoir computers, and neural ODEs. And then we also try to include models that are just widely used for time series forecasting in general. So these are things that machine learning people use, but which aren't necessarily tied to dynamical systems. So we also benchmark things like transformer models, temporal convolutional networks. And then one model that I'll highlight is a model called NBeats. This is a model that generates forecasts hierarchically with separate neural networks. And this is, in the ML community, a pretty strong long-term forecasting model that's been winning a lot of competitions. So in other words, we have classical methods, we have physics-based methods, and then we have these large, arguably very sort of low domain bias models that the ML community uses for forecasting. And we're going to train all of those different models separately on each one of these different dynamical systems. And I'll mention that when designing a benchmark like this, our biggest cost is model selection. There's a lot of free knobs you can turn, especially in the larger models. So a lot of time that we spend is really in hyperparameter tuning before generating the forecasts. Okay, so we have all these different dynamical systems. We have all these different forecasting models, and we want to see if we can get a general sense of what kinds of systems are easier to forecast. Okay, so the first thing that pops out is more or less what you'd expect. which is that a lot of these larger domain-agnostic models perform very well in this forecasting task. And this isn't that surprising because it turns out that our friends in the ML community aren't lying to us. These larger models really do work. But one of the things that's very striking is that some of these large models are very noticeably stronger at long-term forecasting than earlier methods. So for example, NBeats, this model I mentioned earlier that came out a few years ago, this actually pretty consistently does well across these different 135 systems. Yeah, what's up?
That's just the average error across the 135 systems.
Yeah, because it's a little bit bright, but yeah, so these error bars are across 135, yeah.
And on the left there, I'm sorry, it's not very visible. On the left there, there is a hidden, there's a highlighted region on the trajectory and there's a hidden region on the trajectory. What does that mean?
Oh, sorry. So when I train this, so when we do model selection, you use one trajectory, and then you do all your sort of training. Then when you do your testing, you give it as input something it's never seen before. So that's some amount of points. Then you have it forecast something it's never seen before.
That's the forecasted region?
Yeah, and the colors should match up with the models. Yeah.
Thank you. Sorry, it's very bright. It's not
No, yeah, it's the downside of doing white on black for presentations. Okay, and one thing I'll point out is that a lot of the models that do very well at both short horizon forecasting, so getting the next few time points right, as well as long horizon forecasting, so getting very far into the future. That more or less tracks what we'd expect, because if I want to get a long-term forecast of a chaotic system, I probably should get the first few points right. But it still is nice to see that pop up really systematically across these different systems. Okay, so I thought this was interesting, although maybe not that surprising, that these larger models make a noticeable improvement on forecasting chaotic systems. But it got me interested in seeing whether there might be something that these larger models are able to pick up on, that earlier methods that folks were using to forecast chaos, these methods weren't able to pick up on. So in other words, are these models learning something about the physics of the system that wasn't possible before? Yeah, what's up? Yeah. So all of these are, none of these models do the stochastic approximation or anything like that, yeah. Okay, so fortunately for me, a lot of the larger models are trained iteratively, so we can actually watch the process of what happens as these learn to generate forecasts. So what this video shows is the process of training a couple of the deep learning-based models. And I'll mention I'm spacing my snapshots logarithmically, so we get a lot of detail early on in training, but then later my time steps are really far apart, so it gets a little bit crazier. And all I want to emphasize in this video is that for a lot of these models, as they continuously train, so they see more and more data to update their weights, they start out by kind of focusing on the local geometry, so they just focus on getting the next couple of time points right, which tracks with what I would expect. But you'll notice that a lot of them have this almost discontinuous event where they go from just trying to get the next few time points of the local geometry of the attractor right, to really trying to capture this whole shape, right? So they reach some forecast horizon where it's not sufficient to just get the next few time points right, but they really start to couple into the overall shape of the object that they're trying to forecast. And this interested me because it suggested that maybe something about the underlying topology of the object that they're forecasting might couple into their ability to forecast it. So maybe these large models are picking up on something related to the geometry of the underlying system. So this caused my group to start to dig deeper into whether we could quantify the degree to which these models are able to capture the underlying geometry. So it turns out that if you dig into nonlinear dynamics theory, there's actually a very principled way of thinking about the geometric yeah, what's up? No, what's up? Yeah, so I'm not training trajectories finding the attractor, I'm just assuming we were already arrived at it, yeah. So it really is a low-dimensional forecasting problem, yeah.
And is all of the data is always fully observed, so whatever the state space of the system is, you have full observation with no noise of that state of the system.
Yeah, it's not only fully observed, but I'd even say it has an additional advantage, which is that a lot of these, when you do the hyperparameter tuning, it selects a look-back window that's several time points, so it even can lift it, so it has even sort of additional information than just the full state, because it can use past values.
Do you find that it's useful to have for example, a delay embedding when there is in fact a Markovian map? Would you rather still have delays for some reason? What's the story on that?
Yeah, so you're right. So in principle, you shouldn't need any more than the current state because we know there's an ODE that underlies this that in principle is learnable. But in practice, having past values like a time delay, even when you have full state information, helps. So I don't feed that as an explicit feature, but because I have a context length that is larger than 1, implicitly there's something like a delay embedding being used in these models. They're using that information probably to effectively linearize the internal representation or something.
Just one question since we're on the slide. You said that they're essentially learning a local piece of the time series and then extrapolating to the full attractor. Does that just follow from the fact that all of these are being fed sequential data and being integrated from some initial condition, and therefore they need to fit the piece around the initial condition first before they can fit anything else?
Well, I mean, it's tricky because when I do a forecast like this, right, I'm giving it some data, or I'm giving it one epoch of training, then telling it to forecast something it's never seen before, then giving it a little bit more information and telling it to forecast. So it's not like it's necessarily seeing this particular initial condition multiple times. It's more like it's seeing different batches of history data, and that's allowing it to update its weights. Yeah.
So the batches you mentioned, care is taken to have them ordered according to time. It's not just randomly sampling.
Yeah, so I do like both when I do the model selection, I do correct time series cross-validation, so there's no causal leakage there. And then when I do the actual testing, it's fresh data and it never gets to update anything based off of things it's forecasting. Yeah, so I do check stuff like that. Yeah. Okay. So my group is interested in whether we could maybe say something about how this couples to the geometry of the underlying dynamical systems. And it turns out that if you dig into dynamical systems theory, there's a very principled way of doing this that was developed about 40 years ago or so. And this is unstable periodic orbit theory. I think it was co-developed by a few people at the conference, but I'll just give an overview just so it's clear how I'm thinking about it for this problem. So the basic idea is that if I have some dissipative dynamical system, that system's attractor is dense with unstable solutions of the underlying dynamical equations. So a lot of us are probably familiar with things like things like saddle points, which are unstable fixed points. You can think of UPOs or unstable periodic orbits as like spatially extended saddle points, where there are sets of points that are attracting along some directions but repelling along others. And so in the same way that with saddle points, I tend to kind of get stuck at them for a while, then fall off, unstable periodic orbits, trajectories tend to come in, get stuck following the orbit for a while, but because it's unstable, they fall off later. And it turns out that any continuous time ergodic system is dense with these, and I can characterize each one of them by how long I tend to get stuck on it, in the same way that I tend to get stuck on saddle points for different amounts of time. This is potentially a useful way of thinking about dynamical systems, because instead of thinking about them purely in terms of just a bunch of points on some fractal, instead I can say that I have these orbits embedded with the attractor. Those orbits have different relative degrees of stability, and some of those orbits might be more important than others, in the same way that I might get stuck at some saddle points more than others. And there's a whole theory here, but the big takeaway of unstable periodic orbit theory is that if I have a couple of orbits embedded in my attractor that are less unstable than the others, they're the most relatively stable orbits, my dynamics will tend to get stuck on those dominant unstable periodic orbits for really long durations. And so any sort of invariant property that I calculate as an integral over the trajectory, like a dissipation rate or turbulent kinetic energy or something, that can be approximated by its value on those dominant unstable solutions. So you can almost think of these as something like a modal decomposition of the dynamics. Okay, so there are nice algorithms that exist for finding these from time series. To keep an eye on the time, I won't go into this, but I'll just say that you can almost think of this as analogous to an approximation of a probability distribution in terms of modes. Instead, we're thinking about a dynamical system, and I want to approximate it in terms of a couple of dominant orbits. And there's some nice theory in here. Svetanovic's papers go into this in some detail, but basically you can think of this as just an approximation method for dynamical systems that highlights the topology of the attractor. Okay, so UPOs exist in their density of the attractor, and they might tell us something about how complex the underlying geometry is. So my group has developed methods for finding these from time series. We'll skip this. And it turns out if you go across these 135 different dynamical systems, you see very wide variation in the number of orbits that you need to capture the underlying geometry. And this kind of makes sense because if you think about this in sort of a probabilistic view, when I take PCA of some data set, there's often differing numbers of principal components I need to approximate it. In the same way, if I have these different geometric objects, some of them intuitively have more complicated geometries, so it takes more orbits to capture the majority of their variance. So across all these different dynamical systems, I can extract out something like a measure of how complicated the orbit set is. And when I compare that to the forecasting results, it turns out that they more or less explain this drop-off I see, where at some point, rather than the Lyapunov time determining how predictable a system is, whether or not a forecast is successful couples into how complicated this orbit structure is. And the intuition there is that asymptotically, something like the Lyapunov exponent should determine predictability. But when you're forecasting finite data sets with finite models, other things like the topological properties of the underlying data might couple into how effective your forecast is. And this is something my group is very excited about because it's just these large forecast models have some innate ability to learn geometry because they have all these weights. And so there might be ways to use ideas from unstable periodic orbit theory to probe their internal representations. Okay, I'll go ahead and wrap up there, and I'd be happy to take any additional questions. Thank you.